Imagine a machine taller than a 20-story building, a machine that moves millions of cubic meters of air every hour without a single motor, fan, or moving part. Yet this incredible structure prevents entire power plants from overheating and shutting down. Even more surprising, its secret lies in a simple curve hidden within its concrete walls. Remove that curve, and the tower becomes dramatically less effective. So how did engineers discover that a strange hourglass-shaped tower could harness the laws of physics to do the work of massive mechanical systems? And why did these structures become one of the greatest engineering achievements of the 20th century? The story begins at the start of the 20th century, when cities across Europe were growing at an unprecedented pace. Factories expanded, coal mines operated around the clock, and power plants struggled to keep up with the demand for electricity. But with greater industrial production came a serious problem: heat. Every machine generates heat, and the larger the machine, the more heat it produces. Steam turbines, boilers, and heavy industrial equipment all required enormous amounts of cooling water to prevent catastrophic overheating. Thousands of tons of water circulated through power plants every minute. After absorbing heat from the machinery, that water had to be cooled before it could be reused. At first, engineers relied on simple wooden cooling towers. Water flowed through the structures, while air carried away excess heat. The concept worked, but the materials did not. Constant moisture and hot steam quickly caused the wood to rot. Maintenance costs soared, and factories were forced to shut down frequently for repairs. A stronger and more durable solution was desperately needed. The breakthrough came in the Netherlands. Two engineers, Frederick van Iterson and Gerard Kuypers, proposed a radical idea. Instead of using wood, they would build cooling towers from reinforced concrete. However, they faced another challenge. Many industrial sites sat on unstable ground due to abandoned underground mines. Heavy structures risked sinking or collapsing. The engineers needed something that was both lightweight and incredibly strong. Their solution looked unlike anything people had seen before. It was a giant concrete tower shaped like an hourglass, a geometric form known as a hyperboloid. Its walls were astonishingly thin, measuring only about 15 centimeters thick in some places. Despite this, the curved design distributed forces so efficiently that the structure remained remarkably strong. The result was a tower that was lightweight, durable, and resistant to ground movement. Yet when the first towers were tested, another problem emerged. The airflow inside the structures was too weak. The hot water from the power plants was not cooling fast enough. Engineers needed another breakthrough, and the answer came from a simple principle that almost everyone has experienced. Think about a garden hose. Water flows at a certain speed, but when you partially cover the opening with your thumb, the water suddenly shoots out much faster. The same amount of water is forced through a smaller space, increasing its velocity. Engineers realized that air behaves in a similar way. They redesigned the cooling tower so that it narrowed in the middle. As warm air rose through the tower, it passed through this narrow section. The restricted space forced the air to accelerate dramatically. The effect was extraordinary. The tower created a powerful natural draft. Hot air rushed upward like it was being pulled through an enormous invisible chimney. At the same time, cooler air was continuously drawn in from below. No motors were required, no fans consumed electricity. The tower had effectively become a self-powered air pump driven entirely by the laws of physics. The strange hourglass shape was not an architectural choice. It was the key to the tower's success. For years, cooling towers appeared to be nearly perfect. Then, in 1965, disaster struck. On November 1st, a powerful autumn storm swept across northern England. At the Ferrybridge power station, 8 massive cooling towers stood side by side. Each tower was as tall as a 30-story building. During the storm, workers heard a terrifying rumble. Cracks spread rapidly across the concrete walls. Within a short period, one tower collapsed, then another, then a third. 3 enormous structures had been destroyed in less than an hour. At first, many people suspected poor construction or even sabotage. However, investigators uncovered a very different explanation. The towers themselves were not weak. The problem was their arrangement. Because they had been built too close together, they created dangerous wind channels. As strong winds struck the first tower, its curved surface redirected the airflow toward the narrow spaces between neighboring towers. Wind speeds increased dramatically, creating powerful suction forces. The resulting pressure exceeded what the thin concrete walls could withstand, leading to the collapse of 3 towers. The incident forever changed cooling tower design standards around the world. Even after solving airflow issues, engineers faced another challenge. The water inside the towers was not cooling efficiently enough. Large streams of hot water fell like waterfalls from the upper sections of the structure. The droplets were so large that they could not release heat effectively to the passing air. Many reached the bottom while still carrying significant amounts of heat, reducing the efficiency of the power plant. The solution came from a simple observation. Imagine placing a sugar cube into a cup of tea. It dissolves slowly. Crush the same cube into thousands of tiny grains, and it dissolves much faster because the total surface area increases dramatically. Engineers applied the same concept to water. They installed enormous sprinkler systems inside the cooling towers. Instead of falling in large streams, the hot water was broken into billions of tiny droplets. This created an enormous surface area where water and air could interact. Heat transfer improved dramatically, and cooling efficiency increased to levels that had previously seemed impossible. But once again, solving one problem created another. Residents living near large power plants began noticing huge white clouds rising constantly from the cooling towers. On cold days, thick fog formed around roads. In some cases, localized snowfall appeared even when the surrounding skies remained clear. Naturally, rumors began to spread. Some people believed the towers were releasing dangerous chemicals. Others feared environmental contamination. Scientists eventually explained the truth. The white clouds were not smoke or pollution. They were simply water vapor, the same phenomenon visible when steam rises from a boiling kettle. Warm, moisture-rich air left the cooling tower and mixed with colder outdoor air. The moisture condensed into tiny droplets, creating visible clouds, fog, and sometimes even artificial snowfall. To reduce water loss, engineers added special devices known as drift eliminators near the tops of the towers. These systems captured water droplets and returned them to the cooling process while allowing clean air to escape into the atmosphere. Perhaps the most remarkable demonstration of cooling tower engineering came in 2008, when a devastating earthquake struck China's Sichuan province. Buildings collapsed, factories crumbled, and infrastructure suffered massive damage. Yet many cooling towers remained standing. The reason once again came down to geometry. The hyperboloid-shaped distributed stress throughout the structure. Instead of rigidly resisting the forces of nature, the towers flexed slightly and redirected energy through their curved surface. Their design allowed them to survive forces that destroyed many nearby buildings. Today, cooling towers remain one of the most elegant examples of engineering ever created. They contain no giant motors, no sophisticated electronics, and no complex moving mechanisms. Instead, they rely on geometry, physics, and a deep understanding of how air and water behave. Their iconic shape is far more than a design choice. It is a perfect example of how engineers can use the laws of nature to solve enormous challenges. These giant concrete towers stand as monuments to one of humanity's smartest engineering ideas, proving that sometimes the most powerful machines are the ones that allow nature to do the work for us.